What? Namaskar. Welcome to the revision course in real analysis. Okay, so स्वागत है आप सबका. And in this session, we are going to discuss some interesting questions in real analysis. And yes, the very first problem is there in front of you. And it's multiply selective questions. I mean to say, more than one options might be true. So I hope you can try this question. You will try this question and certainly you can do it. Yes, the topic is sequence and series in real analysis. And this very first question, a sequence is given. This is the nth term of this sequence. And thereafter, they are asking about its convergence, its monotonicity, its boundedness, and about its limit. Yes, what will happen if limit n tends to n will approach to infinity? So there are four options, and certainly some results related to real analysis may help you to do this question. Okay, so when you will watch this video recorded, then certainly you can pause the video and you may try, but for now I'm going to discuss it. So first of all, I would like to check the monotonicity. I would like to check whether it is monotonically increasing or monotonically decreasing. After that, I would like to discuss its boundedness, and thereafter we will try to find its limit and tends to infinity. So yes, step by step we are going to understand, and certainly everything will be discussed beautifully. So yes, first of all, I want to see its monotonicity. So you people know that when shall we say this sequence is monotonic? So if we will take this as an, okay, so what is our an? 1 plus 1 over factorial 1 plus 1 over factorial 2, and by doing so 1 over factorial n. And similarly we can write an plus 1. So what we need to do for an plus 1? We will just go one step ahead, isn't it? Yes. So what is our an plus 1? Certainly this is 1 plus 1 over factorial 1 plus 1 over factorial 2, and by doing so 1 over factorial n and plus 1 over factorial n plus 1. And if we really want to see whether it is monotonically increasing or decreasing, then certainly we will find an plus 1 minus an. If this would be greater than 0, then an plus 1 will be greater than an, and it will imply something. If this is less than 0, then certainly it will imply something interesting. So let's see what the thing is going to happen. So in the similar fashion, you can see an plus 1 minus an was there, and here is a minus sign. So certainly all these terms will be cancelled, and finally this 1 by factorial n will be certainly cancelled with this also, because this term is up till 1 over n plus 1 factorial. So finally we will be left with 1 over n plus 1 factorial, and n is the natural number. That's why certainly this will be strictly greater than 0. So what happens if an plus 1 minus an is strictly greater than 0? This implies an plus 1 will be strictly greater than an for all naturals. And that's why this is monotonically increasing, because if you are going to put n is equals to 1, then you will see a2 is greater than a1. If you will put n is equals to 2, n is equals to 2, then we can see a3 will be greater than a2. N is equals to 3, then a4 is greater than a3, and by doing so. So that's why this is what? Monotonically increasing sequence. Okay, the next thing is what? So this option is absolutely right. Actually, all the options are true, but how? It will be really interesting to see. So it is monotonically increasing. Now we are interested with its boundedness, whether it is bounded or not. And for that, what shall we do? We have written an is strictly less than 1 plus 1 plus 1 by 2 plus 1 by 2 a square. Why? Because what is our an actually? Our an is what? 1 over 1 by factorial 1 plus 1 by factorial 2, and after this there will be 1 by factorial 3, and factorial 3 is what? 3 into 2. But in place of this 6, if we are going to write 2a square, then certainly 4 will be lesser than 6. And that's why in place of factorial 2, in place of factorial 3, when we are going to write 2a square, then certainly this reciprocal will be greater. And that's why a sign of inequality is over here. Okay, because in an, what the things are there? What the things are there? 1 plus 1 by factorial 1 plus 1 by factorial 2 plus 1 by factorial 3 and so on. Okay, so these three terms are similar to this, but in an it was 1 upon factorial 3, it means 1 over 6, but here we are taking 1 over 4. Okay, so lesser denominator implies that this term will be strictly greater than this an, and we can see a pattern over here, and this pattern recall something interesting. Yes, what? Certainly the geometric series from here onwards. You can see this is a geometric series, and some of the geometric series, the formula is over here, and finally we are over here, because this will be 1 by 2, 1 is already here, and after that a geometric series can be seen easily, and thereafter we are going to see this one, 1 plus 2 minus 1 over 2 to the power n minus 1. And as n tends to infinity, then certainly this will go to 0 if n tends to infinity. So we can say what? We can say what? But this will go to 0, but that is there is no necessary for that analysis. We can simply say that this is 1 plus 2, which is 3, and 3 minus something. 3 minus something, this quantity is less than 3 for sure. So that's why this is strictly less than 3. So we can say that our sequence is bounded above by 3. So if your sequence is bounded above and monotonic, then certainly it will be what? Convergent, and it converges to its least upper bound. So certainly it will converge at less than or equal to 3. So that's why we can say that limit n tends to infinity, an is less than or equal to 3. So that's why this option A is correct. And now for the boundedness, we can see one more thing, that an is greater than or equal to 2 for all n, this is given. And if I will take the limit n tends to infinity an, then that will be greater than or equal to 2 for sure. So here we can see that limit n tends to infinity an is greater than or equal to 2. Limit, what can we see over here? That limit n tends to infinity an is greater than or equal to 2, but less than or equal to 3. And yes, it is convergent. Okay. And bounded, and the limit also lies between 2 to 3. So that's why all the options are absolutely correct. That's why all the options are correct. Okay, so I hope this is clear. Now we are going to discuss now let's go to discuss the second question. Okay, question number 2 is there in front of you. Yes, this is the question over here. This question is also interesting. You can see A and B are two positive unequal numbers. They are saying that A is not equals to B. Okay, an, bn are defined as, how this an is defined? Okay, an minus 1 plus bn minus 1 over 2. So we can see the arithmetic mean of these two terms, and bn is equals to under root an minus 1 into bn minus 1. So certainly this bn is the geometric mean for n greater than or equal to 2. Then once again, this is more than one correct wala question. Multiply selective question is there in front of you. And once again, you have to check its monotonicity. And you can really understand why this series is called doubt killer series, because you have to check whether it is monotonically increasing or monotonically decreasing, or the option C is what, one of an and bn are monotonically increasing, and the sequence and the sequence bn converge to the same limit. So here are four options. You may pause the video if you watch it, if you are watching it recorded, and thereafter you can answer, but for now I am going to discuss it beautifully. So first of all, I would like to say certainly these sequences are monotonic, but which one is monotonically increasing and which one is monotonically decreasing is really interesting. So first of all, I would like to say option C and D are the correct answer for this. One of an and bn are monotonic increasing. दोनों में से कोई एक monotonically increasing होगा, but an is not monotonic increasing. We will see it. And one more interesting thing is what, both the sequence converge at the same limit. So we are going to see all these things. So first of all, let's see the monotonicity, and for that we are taking a case that a1 is strictly greater than b1. We are taking what case? A1 is strictly greater than b1, and for any two positive numbers, the arithmetic mean is always greater than or equal to geometric mean. We cannot forget this result, that the arithmetic mean will be greater than or equal to geometric mean. Okay, and we had already taken a1 strictly greater than b1. Okay, and by using, we can say an strictly greater than bn for all n. All right, and an plus 1 is what, the mean of an plus bn, because it was given, I think, yes. So if we will place n plus 1 in place of n, then in that case it will become an plus 1 is equals to half of an plus bn. Okay, and that's why we have written this. And from this case, a1 is strictly greater than b1, and that's why if we will replace this bn by an, then certainly this strictness in inequality will occur for sure. So that's why this inequality. So this implies what, an plus 1 is strictly less than an. How? Because this is what, 2an divided by 2. So this is what, an. So hence we can see an plus 1 is strictly less than an. What does it imply? It imply what? If we will put n is equals to 1, then a1 will be greater than a2. If we will put n is equals to 2, then a2 will be greater than a3. So that's why. So hence we can see what, as we go ahead, the terms are decreasing, isn't it? A1 is greater than a2, a2 is greater than a3, a3 is greater than a4, and so on. So that's why this sequence an is what, monotonically decreasing sequence. Okay, so in the option 1 we have written an is monotonically increasing, so that's why this is wrong. Certainly an is monotonic, but it is monotonically decreasing, so that's why. Now let's see for the sequence bn. Bn is also monotonic, but we will see that Bn is monotonically increasing. So that's why this option B is also not true. So let's go for the second option. All right. So hence we can see that uh, this is monotonically decreasing. But for Bn, Bn plus 1 will be is given under root An into Bn. And if we will put Bn in place of An, then according to the case, An is strictly greater than Bn. So if we will replace this An by Bn, then this will be strictly greater than what? Under root Bn into Bn. So this is what? Bn squared to the power 1 by 2, because under square root these things are over here. So Bn squared to the power 1 by 2 will be what? Bn. So hence we can see what? This is monotonically increasing, not decreasing. Sorry. This is monotonically increasing. Why? Because Bn plus 1 is strictly greater than Bn. So if we will put n is equals to 1, then n 1 plus 1. So this is 2. So B2 will be greater than B1. And if we will put n is equals to 2 over here, then 2 plus 1, 3. So B3 will be greater than B2. So hence we can see what? It is monotonically increasing. Okay. So Bn is monotonically increasing. An is monotonically decreasing. It is quite clear. And now we can see what the things were given. An is equals to half of An minus 1 plus Bn minus 1. And it will be strictly greater than half of Bn minus 1 plus Bn minus 1. Why? Because An minus 1 is greater than Bn minus 1. So when we are going to put Bn minus 1 in place of An minus 1, then this strict inequality holds good. Isn't it? Yes. And this is what? 2 into Bn minus 1 divided by 2. So this is what? Bn minus 1. So from here it is quite clear that An is strictly greater than Bn minus 1. All right. So, and in the same fashion, if we will move ahead, then finally we can see what? Finally we can see what? It's very interesting. An strictly greater than Bn minus 1. Yes, this is the thing over here. An is strictly greater than Bn minus 1. So if we will put n is equals to 2, then A2 is greater than B1. If we will put n is equals to 3, then A3 is greater than B2. And by doing so, we will get this one. So from here it is quite clear that An is strictly greater than B1 for all n. And since the sequence An is bounded below, isn't it? From here it is clear that for every natural, An is strictly greater than B1. So this implies what? An is bounded below. And earlier we had seen that it is monotonically decreasing. So it is monotonically decreasing and bounded. That's why it is convergent. And convergent to what? Greatest lower bound. Yes, it's a theorem. If you have a monotonically increasing sequence which is bounded also, then it tends to its least upper bound. If you have a monotonically decreasing sequence and it is bounded also, then it tends to its greatest lower bound. So that's why it's convergent. Now, if we have Bn is equals to under root An minus 1 into Bn minus 1, and if we will replace this An minus 1 with Bn minus 1, then under root Bn minus 1 into Bn minus 1, this will be what? This will be what? I think I must write An minus 1 over here, and thereafter this inequality holds good. And An minus 1 ka whole square to the power 1 by 2 will become what? An minus 1. So from here it is clear that Bn is less than An minus 1. This is the thing. And we can see it easily. And Bn is strictly less than A1 for all n. So from here it is clear that Bn is bounded above. Okay. Bn is bounded above. And earlier we had seen what? It is monotonically increasing. So the sequence Bn is bounded above and monotonically increasing, so it will tends to where? Its least upper bound, isn't it? So that's why, yes. So it is clear that Bn is monotonically increasing and bounded, so it will converge to its least upper bound. We had also seen that an sequence an is monotonically decreasing and bounded, so it will tends or it will converge to its greatest lower bound. And do you know what is the most interesting thing? The greatest lower bond of an and the least upper bond of bn, both will be same, both will be equal. Yes, this is the interesting part, and that's why this option D will be correct. But how? Let's see. Okay, so let's see. This was the given thing. An is equals to half of an minus 1 plus bn minus 1. We had seen that the sequence an and bn both monotonic and bounded. So we can write this 2 will go over here. So 2an is equals to an minus 1 plus bn minus 1. If we will replace this n by n plus 1, then 2an plus 1 is equals to an plus bn. And if we are going to take limit, then what the thing is going to happen? 2 into limit an plus 1 is equals to limit an plus limit bn. And limit an is what? L, and limit bn is what? L dash. Okay, because we have to prove L is equals to L dash, but before that we had proved that the sequence an is monotonically increasing and bounded, sequence bn is monotonically increasing and bounded, both are convergent. We had taken an converges to L and bn converges to L dash. Then we can see a beautiful result over here, that 2L is equals to L plus L dash. And if we will take this into this side, then 2L minus L is equals to L dash. So hence you can see this is L where the sequence an was converging, and this is L dash where the sequence bn was converging, and both are equal. So that's why this option D is also correct. So hence we can see option C and D are the correct options. Now let's go to discuss some interesting things that helps us to find the convergence sometimes, that helps us to find the limit sometimes, that helps us to get 3 marks sometimes in CSIR net or IIT exam, that helps to get marks for GATE exam also. So first of all, I would like to recall, okay, I had already completed real analysis on this channel, but first of all I would like to recall this Cauchy's first theorem and second theorem, and thereafter some beautiful questions are waiting for you. So if you have a sequence an and this sequence converges to L, and then a sequence xn which is the arithmetic mean of n terms of an, okay, which is the arithmetic mean of n terms of the sequence an, then if your sequence an will converge to L, this implies this arithmetic mean will also converge to L. Once again, let me repeat it clearly. If you have a sequence an which is a convergent sequence and converges to L, then if you have a sequence xn where xn is the arithmetic mean of n terms, arithmetic mean means a1 plus a2 plus a3 plus an over n, then this sequence xn also converges to L. So this is the first theorem. But what is the second theorem, which is more interesting? Let's see. If you have a sequence an of positive terms, remember we are discussing it for the sequence of positive terms, then if limit n tends to infinity an raised to the power 1 by n is equals to limit n tends to infinity an plus 1 over an, provided the limit on the right hand side exists, whether finite or infinite. So existence of limit is necessary, but these two things are equal to each other. This is really interesting. This is really interesting that these two things will be equal to each other. So with the help of another, we can really find the first one, okay, or whatever the thing is necessary, needed. So if you are given this limit n tends to infinity factorial n raised to the power 1 by n, then what would you like to say? So certainly we will use this limit n tends to infinity a n raised to the power 1 over n is equals to limit n tends to infinity a n plus 1 over a n. Sometimes it is easier to calculate this, and that's why if you have to get this limit, then certainly we are interested in the ratios. Okay, so that's why limit n tends to infinity factorial n raised to the power 1 by n, this will be equals to limit n tends to infinity factorial n plus 1 over n factorial. So this n plus 1 factorial will be equals to what? N plus 1 into n factorial. These two will be cancelled, but this n tends to infinity will take you to infinity, and that's why infinity is the right answer for this. Okay, so here you can see how this second Cauchy theorem helps you to find this limit for sure. Now let's go for the next question, which is really interesting. If xn is equals to 2 over 1 to the power 1, 3 over 2 to the power 2, 4 over 3 to the power 3, n plus 1 over n to the power n and whole to the power 1 by n, then what would you like to say about limit n tends to infinity xn? What would you like to say? So for this, what do you think? What are the things we are going to do? Certainly you can see something over here. And its power, the whole power is what? 1 over n. The whole power is what? 1 over n. And very soon the Cauchy theorem, Cauchy second theorem will come to help you for sure. So how this is going to happen? First of all, I have written this an. An is what? The nth term of the sequence, whatever the things were there. Okay, this is our an and raised to the power what? 1 by n. So this could be written as what? An raised to the power 1 by n, isn't it? Yes, this is the thing. And the theorem says what? If you have this thing, an raised to the power 1 by n, then this could be written as limit n tends to infinity an plus 1 over an. And that's why what the things is going to happen. It's really interesting. So this is your an. Now we are interested in the ratio, and that's why an plus 1, 2 over 1 raised to the power 1, 3 over 2 raised to the power 2, 4 over 3, and we will go one step ahead for an plus 1, and that's why this is the thing. And we are interested in the ratio because we have to use the statement of Cauchy's second theorem, and that's why an plus 1 over an. So what the thing is going to happen? Every terms will be cancelled except this last term, isn't it? When we are going to take an plus 1 over an, and so you can see the things easily. So this is what n plus 2. So this could be written as n plus 1 over n plus 1 raised to the power n plus 1. This n plus 1 over n plus 1 will give you 1, and this 1 over n plus 1 will be over here, and whole to the power n plus 1 can be seen easily. So from here, limit n tends to infinity an plus 1 over an is what? Limit n tends to infinity 1 plus 1 by n plus 1 raised to the power n plus 1 is what? E. Because we cannot forget this formula that limit x tends to infinity 1 plus 1 by x to the power x is equals to E. A very fundamental formula. So from there it is E. So here E is the right answer. So E is the right answer. Okay, so by using Cauchy's second theorem, we were it was very easy to get the limit. Okay, so certainly this problem series will be continued in this channel, and we'll see you tomorrow with some more interesting problems. Certainly, we will try to complete this real analysis once again, but only the problems you can say, because this course has already completed on our channel. Okay, so you can watch the complete course. I think it's of 100 hours course. You can check out the playlist as well. We'll see you tomorrow. Till then, take care. Bye bye. Good night. Jai Hind, Jai Bharat.